Hello, my name is Selena Wu, and this is my presentation for the magnetic field of a bar magnet lab. Experiment introduction. The purpose for this experiment is to determine the magnetic dipole moment mu of a bar magnet. To find this, I used a magnetometer app on my smartphone to measure the magnetic field at various distances from a bar magnet. I lined up the magnetometer with magnetic north, where B sub x was approximately 0, and oriented the bar magnet such that its axis is aligned east to west, making the magnetic field from the magnet orthogonal to that of the Earth's magnetic field. I made sure there was no other magnetic fields interfering by verifying that the magnetic net field value was approximately 50 microteslas, which is similar to the expected value of 49 microteslas in Atlanta, Georgia. In this experiment, we measured the distance of the bar magnet from the magnetometer when the magnetic field value in the x direction was 20, 70, 120, 170, and 220 microteslas. Additionally, we find the distance of the bar magnet from the magnetometer at an angle of 45 degrees from the x and y axis when the magnetic field value was 100 microteslas. From the data, it can be determined that mu, magnetic dipole moment, is 3.48 ampere meters squared. Observations and physical principles used. It can be observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. This is due to the fact that the magnetometer is already calibrated to make magnetic field in the x direction near zero in the absence of a magnetic dipole. It can also be observed that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. This is due to the distance dependence of magnetic fields, as shown by the Biot-Savart law. To solve for the charge of the tape, we can apply the Biot-Savart law that provides the equations for the magnetic field due to a magnetic dipole, as well as the distance dependence equation for the magnetic field of a bar magnet. We may set these two equations equal to each other and solve for mu, magnetic dipole moment, when the value for n is close to -3. When n is approximately -3, we can cancel out the distance r in both equations, allowing us to solve for mu. Finding mu, magnetic dipole moment. We graph the natural log of the magnetic field in the x direction and the natural log of the distance r to get an equation that expresses the distance dependence of the magnetic field. The slope in this equation represents n, and the y-intercept represents ln of k. We solve for k to be 6.97 times 10 to the -7, and since n is approximately -3, we plug k into the equation below and find that mu, magnetic dipole moment, is 3.48 ampere meters squared. GlowScript code. The GlowScript code demonstrates how we reached our result, firstly by listing physical constants and the magnitude of the magnetic dipole moment, mu mag, as found through our calculations. And we create a gray cylinder that represents the bar magnet. We also have a function, dipole B, that calculates the magnetic field of a dipole given the mu and r, following the equation listed below. Next, we set the observation points at 2 points on axis from the bar magnet along the x-axis and at 4 points perpendicular to the bar magnet along the y and z axes. The code below creates and displays all 6 arrows that represent the magnetic field on axis and perpendicular to the bar magnet, with the on-axis magnetic fields in orange and the perpendicular magnetic fields in cyan. They call the previously shown function dipole B to calculate the magnitude of the magnetic field at each position and then display the value. Lastly, we display the magnetic field at 45 degrees off axis, again using the dipole B function to calculate the magnetic field at the distance when the magnetic field was measured to be 100 microteslas by the magnetometer. This is shown by a magenta arrow. The magnetic field at an angle 45 degrees from the x and y axis and at a distance of 0.3 meters as calculated by the computational model is 4.56 times 10 to the -6 teslas in the x and 1.37 times 10 to the -5 teslas in the y. Additionally, you can see the perpendicular cyan arrows pointing in an opposite direction to that of the on-axis orange arrows. The cyan arrows represent half the magnitude of the orange arrows. Reflection. If I hadn't oriented the experiment to compensate for magnetic north, the measured distance of the bar magnet from the magnetometer would be less than the actual value when the magnetometer read the magnetic field values of 20, 70, 120, 170, and 220 microteslas. Therefore, our bar magnet would appear to be stronger than it actually is, since the magnetic field of the Earth would also be contributing to our measured magnetic field values. We would thus have a larger mu value. If the experiment was conducted with 2 identical magnets, the distance measurements would be less than that of just one bar magnet. Since 2 magnets would create a stronger magnetic field, the bar magnet would have a greater mu value than that of just one bar magnet. Additionally, the magnetic field at a 45-degree angle off-axis, as calculated by the computational model, is similar to, but smaller than the actual value expected and produced during the experiment. This is likely due to the magnetometer not being 100% accurate, but still very close. Finally, we reach the result of this lab to be that the magnetic dipole moment of the bar magnet is 3.48 ampere meters squared.